Very few violins built before 1750 have reached us with their original dimensions. In fact, it took almost 2 centuries before the violin family, which first appeared in Italy at the end of the 16th century, adopted standard sizes across Europe. During the standardization, instruments that fell between 2 standard sizes were often reduced to fit into the smaller one. One way to do this was a width reduction. Basically, a slice of food was cut out of the middle of the instrument and the two halves were glued back together. As you can imagine, this left traces, and particularly on the contour lines. If you look at them, you will see that originally they were rounded, almost U-shaped. But after the reduction, they became sharper, more V-shaped. The question that now arises is the following. Can we automatically identify violin reduction? More specifically, can we detect width reduction by analyzing contour lines? It is an important question in musicology because in the collective imagination, the best violins were not those that innovated, but those that followed the tradition. But in reality, many Baroque violins, including masterpieces by Andrea Amati, were reduced and modified, although documentation about these interventions is scarce. To explore this, we are essentially working with about 40 instruments from the Musical Instruments Museum in Brussels. However, since we cannot manipulate museum artifacts freely, we digitize the entire corpus using photogrammetry. The result is a set of highly accurate 3D meshes with sub-millimeter precision on which we can perform detailed analysis. The next step was to slice each 3D mesh every millimeter along its height in order to extract contour lines. Then, we focused on the bottom part of these contour lines. That's where the U or V shape is most visible. We then fitted these shapes with parametric equations, which are nothing but parabola-like curves. Eventually, we could derive an ID card for each instrument of the corpus. On these examples, we can clearly see the difference between a reduced and non-reduced instruments, both in the shape of the contour lines and in the parameter profiles. Ultimately, we applied a machine learning technique called support vector classification to these profiles to automatically identify reductions. In some cases, the model could even reach extremely high accuracy, even up to 100%. In conclusion, we developed a promising classifier based on interpretable features to identify width reductions. Next steps are to extend this approach to length reductions, which affect other morphological aspects, and eventually to build a tool that could even predict the original size of reduced instruments.